Okay, hi, welcome to lecture 3 of machine learning. Let's do a bit of Q&A because I see some questions. Um, Homework 0 indeed is not graded. There is no benefit to submitting other than just checking your understanding of the material that you need for this class. So we very possibly will grade. I think it's unlikely just because of cycles. I think it's more, we'll have the rubric and the results up and also sort of the solutions up so you can take a look. I think we're planning to release the solution pretty quickly, so I'm not sure that you can submit in a few days. So I would say don't look at, actually, I'm not sure you have a choice to not look at the solution. Forget, I'll take another look at how it's set up, but I think it might force, once we release the solution, you can just see it once you look at the questions. Any other broad setup questions for the class? Okay, so let's jump into material. I'm trying a third new thing today. If there's feedback as we go along, please let me know. I'm using a different PDF viewer that hopefully can allow me to write more easily, but I guess let me know as we go along what's working and not working. Okay, so last lecture we talked about linear regression. I'll talk about homework. Well, if you can't, apologize, let me switch gears quickly. If you can't see homework 0, could you ask a Piazza question and we'll try to figure it out on there. So last lecture we talked about linear regression. And in particular, we talked about ordinary least squares, and hopefully sort of fresh in memory, this last Friday. We talked about ordinary least squares as a standard way for trying to solve our regression and classification problems. So a quick reminder for everyone, or I guess a question. So if you recall, the solution of ordinary least squares, so the problem that we're trying to solve is y minus x w L2 norm squared. Those should be 2, and we're trying to minimize sorry, this is a complete mess. Okay, that's not working. Okay, so I may not try this again. I'll probably try something else next time. Apologize for the tedious. Anyways, they're trying to minimize over W of the L2 norm difference between y and xw, and we said that w star is equal to x transpose x inverse x transpose y. Right, so remember from last lecture. So this is our ordinal least squares estimate. Now, we said that this estimate doesn't always exist. Can someone remind me when this estimate may not exist? What might cause it not to exist? Okay, so it's correct. So I see lots of right answers. So the estimate may not exist because we have to solve this inversion. And if this inverse doesn't exist, then the estimate doesn't exist. And so the inverse may not exist if x transpose x is not invertible. Question for the class for folks that might have seen this before. So whether or not a matrix is invertible, so this matrix x transpose x, depends on its rank. Maybe a quiz question. So in terms of invertibility, what is the better situation? So remember, this matrix X is of size, Sorry, this writing is messier than I thought. The size n by d. Okay, so it's an n by d matrix. So X transpose X is a matrix of size what? Does anyone know? Okay, so D by D, correct. Okay, so if, sorry. So suppose D is bigger than N. Sorry, D is, yeah, much bigger than N. Versus D is less than N. Which situation is better for this matrix being invertible? So is it better, think of this as data matrix, is it better if it's sort of tall and skinny or if it's short and wide? Okay, so in general, I see lots of correct answers here. If D is less than N, that's a better situation, so this is better. Why is that a better situation? So why is it better that the number of dimensions is less than number of samples? Yeah, so once D is greater than N, can anyone else? Okay, so that is correct, but I'm looking for a linear algebra type or a slightly different solution. Both answers that are up so far are actually correct. Okay, so if D is greater than N, so it's gonna boil down to the rank and linear independence. So that ends up affecting whether or not this matrix is invertible. So if you have many, many more features than samples, then you end up in an invertibility problem. So that's one of the cases that will definitely break the invertibility of this matrix. So I think many of the answers there look correct to me. Okay, so let's move on. So when this estimate doesn't exist, what are some alternative solutions? So we talked about a couple. Okay, so we talked about pseudo-inverse. So instead of using the regular inverse, use a pseudo-inverse, and then we'll talk about regularization. Great, thank you. Okay, the other thing we talked about last lecture was least squares classification. So does anyone remember how we can use least squares regression, but apply it for classification problems? What's the process? So there are two steps. All right, so step number one, I'm seeing, so the answer. So step number one is solve the regression problem. Regression. I'm finding this much harder to write with. I apologize. This is looking much worse. So I've learned a new lesson today. It should be G. Okay, so solve the regression problem, which gives you a W. And then step number two, you have sine of W transpose X as the new prediction. So you solve the regression like before with standard least squares. And then for the final prediction, you use a threshold. So you take the threshold of whether the prediction is positive or negative, and that becomes your prediction. So that's the strategy that we came up with for using least squares for classification. So this distinction is important because, again, the least square setup is solving a squared loss problem, and it's developed for regression problems. However, what we said is that it ends up working okay for classification. That's a good thing to know, that you can use least squares type solutions for classification. And what's really nice about least squares is that it's very easy to apply, very easy. It's sort of built into most packages, so it's very straightforward to use and apply. So it's good to have in your toolbox as a sort of first cut, simple approach for solving many kinds of problems. We'll dig a lot more into least squares, regression and least squares for classification today over the next few slides. Okay, and finally, I'll just answer this very quickly. So we talked about what the issues might be for using least squares for classification. So the main issue is that it's developed for regression, so it's trying to directly fit the target, whereas what we want is to make the right classification decision. And today we'll talk a bit more about the issues that can come up when we're using this kind of loss function, this kind of setup for a classification task. Okay, so the main topic of this lecture is logistic regression, and then we'll develop it and then we'll contrast it with least squares for classification. And so for all of the lecture today, we're going to focus on classification tasks. So in classification tasks, your goal is to fix a function that takes an input and spits out an output where the output is some label. And for convenience, we're just going to fix the label as either +1 or -1. What matters is that the label is binary, so it only takes two possible states. It'll turn out to be convenient to use +1, -1, but any choice of binary target is fine. So they're equivalent. You can transform between any binary target and any other one. For our purposes, though, it will be convenient to use +1, -1 for most of the discussion. Okay, so the goals of this lecture would be to understand logistic regression. But before that, I apologize, I forgot that we're going to cover this. So before that, we're going to cover feature construction based on an application. After this, we'll go back to logistic regression and work through some of the details, and then try to contrast logistic regression with least squares for classification to see what's similar between the two approaches for solving classification problems and how they're different. Hopefully this gives a bit of a better understanding of how these two methods are related to each other. And hopefully we'll also set up thinking about machine learning, supervised machine learning problems more broadly beyond these two settings. Okay, you can see most of the material for this lecture in chapter 8 of the Murphy book. There's notation, just gonna put it up, you can find it in the slides. Okay, so let's talk about constructing features. And we're gonna do this via an example. So we're gonna think about the task of boundary detection or edge detection. So if you're not familiar, the task of edge or boundary detection is given an image. I want to find the boundary between, say, the foreground and the background, or the boundary between objects. So if you like, I want to be able to tell apart different parts of an image. So for instance, if I'm interested in figuring out the boundary between the person and the background, then you might want to be able to draw a line that sort of roughly looks like, the top is not right, but it roughly looks like this around the whole image. Now, how might I pose this edge or boundary detection task as a machine learning task? What is my input X and what is my output Y? Any guesses on how I can convert this task into a prediction task? Okay, so X could be, for instance, pixel intensity. So based on the comments, I'll just specifically mention, actually, can someone tell me why first before I answer or I comment on the X choices so far? So X is something related to pixels. And Y? Okay. So Y can very simply be, if we're interested in just two, like foreground, background classification, so object versus not object, we can just make it a binary task. So we can simply make Y +1 -1, where this might be foreground and this might be background. Okay. I'm going to erase that second one. That doesn't look like anything. Okay, so hopefully that's clear. So I can, if I'm interested in more than 2 classes, some folks are going ahead of me. So the simplest version of the problem is, given a pixel, can I tell whether it's foreground or background? So that's the sort of simplest definition of the problem. And we'll try to build up complexity and make this a bit more sophisticated as we go along. So if I can tell whether it's foreground or background, or sort of object versus background, then I can sort of tell for every pixel, I can give it a label to put it either on the sort of one of the 2 classes. Another formulation that's also reasonable for this task is, I'm not interested in saying foreground, background. I'm instead interested in saying whether a certain pixel is at the boundary. That's also a common way of trying to set this up. So it's a slightly different classification problem, but again, this would be a binary task. Okay, got rid of that. And here I'm simply interested in boundary or not. So boundary or not boundary. And that is another sort of definition of the task that might be reasonable. So suppose I wanted more than 2 classes. Suppose I want to tell apart the shirt, the jacket, the face of in this picture. How would I modify the problem from what I've just described? So any guesses? So I'm exactly. So there's an answer in the chat. So instead of having just 2 labels for the 2 cases that I'm considering, I can have multiple potential outputs. This makes it a multi-class problem. We'll spend a lot of time in the next few lectures talking about multi-class. I just want to mention that now, just to give some context. For now, let's say we're solving a simple binary classification problem. So for every pixel, we are going to just assign it to one of 2 classes. You can use either definition that you like. Both of these are roughly equivalent for what we care about. So I'll put an or. I can either try to solve this as a foreground, background type of task, or I can try to solve it as a boundary versus not boundary. So I made a bad choice in PDF viewer today. Sorry, I know I keep repeating it, but I didn't expect it to be this bad. Anyways, so yeah, that's not much better. Okay, so in particular, though, I'm not just extending the length of y, though I think what you mean when you say extend the length of y is that you have more possible output, more possible states that y can take. So if that's what you mean, then that's sort of appropriate. So what does it mean to be foreground or background? So this is a person standing in front of, a person standing in front of, I guess, a wall. Maybe, I'm actually not completely sure. So a foreground would be what's in front, and a background would be whatever is behind. That's a standard problem that you might be interested in solving in a computer vision test, for instance. So we haven't talked about, say, details of how I would, say, construct the data set and things like that. The definition, if it's a single object in a scene, typically foreground, background is sort of obvious. It's just whatever object you're interested in versus whatever's behind the object. You can, of course, make this quite sophisticated if you want. For now, we'll take the very simplest definition. In fact, maybe cleaner for many of you would just be think about, all we want to do is detect the boundary. So we want to know the boundary between objects, and that's the task that we're interested in solving. Okay, so there are potential issues with trying to solve this task in real settings. So the square is highlighting a very obvious issue where the color of the jacket exactly matches the background. And so it's without additional cues, you can't tell just by looking at a pixel whether this pixel happens to be in a background pixel or a foreground pixel. And this is true to the eye, but in this particular sort of low resolution example, this is also true in terms of the actual pixel intensity. So the value that the pixel takes, this is the three-dimensional RGB value. The intensity of that value looks the same for both the background and the jacket. There are other issues that can come up. So can anyone highlight maybe the issue that shows up if I'm interested in trying to do boundary detection or foreground? So shadows and shading are definitely a problem, and other issues that can come up. So what's the issue in this third one? Yep. So if you have texture in the image, then texture makes it much harder to tell foreground or background. So to be even more maybe pedantic and precise, so what I'm showing are a set of different sort of regions from images. These are all images that have that either have a boundary or don't have a boundary in them. And so in each of these images, what the line is sort of one-dimensional line through the image, and the value on the right, so this is image, and this is pixel intensity. Oh God. Okay, pixel intensity. This is very slow. This is image. Okay, so I just drew a line through the image. So I'm just going sort of across this line, for instance. This is hard to see, but say across this line. And across this line, I'm going to do the pixel intensity sort of across the whole line to see what the pixel intensity looks like. So this is pixel intensity. Yeah, in all these images, this is the center line. So if you like, the center line through the image and pixel intensity as you go through. And what you would like to see is that when you go across an edge, so if you go from, say, a background to a foreground, or any other kind of edge in the image, that the pixel intensity looks very different across the edge. So maybe a good example of this would be something like this picture here, where you might argue that I could tell that there's likely a boundary around the center because the pixel intensity looks very different from one side versus the other. Whereas in many other images, particularly images like this texture image, you can see that the pixel intensities look sort of roughly the same on both sides. And so there's not enough signal in pixel intensity by itself to tell whether there's an edge in that particular image. So I normally would do this as a quiz, but I guess I just sort of gave some of the answers away. But the key takeaway here is that if I just look at an image, I cannot tell, so boundary images versus non-boundary images, the pixel intensity values will look sort of roughly similar. What about the top right image? So we're going to go into detail about how we might try to solve this problem, or alternative to looking at pixel intensity. So that's what we're going to build up to as we go through the next few minutes. So the main takeaway here is, again, I'm trying to solve this problem function from pixel to label. And if all I have as my information, all I choose is the pixel intensity, this problem will be hard to solve. So this problem will not, I will be able to solve this problem accurately. So again, the picture on the left is, for every column, the picture on the left is an image. Actually, I can just go back. Okay, so for each one of these, okay, so the picture on the left is an image, picture on the right is pixel intensity along the center of that image. Okay, so the main takeaway here is that looking at the intensity is not necessarily a good indicator for where the boundary is. So clearly this is an issue. Okay, so now one could imagine what other cues could I add as additional information to make this edge or boundary detection or foreground background detection easier to solve. And I already see lots of good answers. So I'm going to talk about some of the methods in now, I guess, oldish paper, but not that old, by Martin et al. You can just Google Martin et al. Learning to detect natural image boundaries, and it'll give you the paper if you want to learn more details. But you can do a bunch of simple things. You can get brightness gradients. So this is the sort of the difference in brightness across the image, and add measure and keep that. You can do color gradients. So this is difference in color across as you go across the image. Difference from brightness is that brightness is all of the channels together. Color is potentially each channel by itself. So using a standard RBG type of coding, like we talked about in the first class. I can look at texture, so I can have a sort of texture extractor, extract local textures, and then look at how that texture changes across the image. So you can do a bunch of these kinds of things, extract a bunch of features. And what is nice is that if I just look at these features by themselves, so what I'm doing here is I've taken a bunch of images. I've extracted these features at every pixel for all these images. And then I have drawn these features as images themselves. So there's a question about intensity versus brightness. So I'll leave the details of how you would encode texture. You can use standard, well, the short answer is I can use standard texture extractors. The longer answer, I'll just leave the details either to office hours or a quick chat after, or you can look up the paper. But there's standard tools for extracting textures from images. Intensity and brightness, here we're thinking of them as the same thing. So that's not important here. What's important here is that you actually need many of these features together. So the question is, can we overlap these different gradient images? So we're going to use a slightly different method that's not overlapping. So we're going to take all of these images and we're going to essentially concatenate all of them. So if you look in the slides, so BG is brightness gradient. TG is, I think it's texture gradient, and then color gradient. So, okay. So I apologize. This is covering the notation. But the next question is, how do I combine all these cues together? So someone mentioned potentially just maybe stacking them. Well, I think overlapping them. What we're going to do is stack all these different features together. So in particular, we're going to use a linear combination of all these features. So just like before, or just to be precise, our label is going to be annotated pixel label. So foreground and background, if you like, or edge versus not edge. So we're going to just make this simple binary task. Our inputs, our X is going to be the pixel. So just whatever value for at a particular pixel. And now we're going to construct a new feature, which is going to take our X and spit out a new vector. And this new vector can be any set of things that we've computed locally around X. So it's going to be a vector of features computed locally around a pixel, things like intensity, texture gradient, oriented gradient, a bunch of other features. So sort of, if you think about, these are standard things that you might want to measure for an image, say in a computer vision task. So here what we're doing is we're essentially computing a large set of these and then combining them all together. And we're calling this computed set a feature set. So we're going to call this phi of X. And now we're going to solve our classification problem using phi of X instead of X. So now our prediction problem is going to look like f of X, our prediction, is going to be we're going to stick with linear functions, but now instead of a linear function of x, it's going to be a linear function of phi of x. The phi of x is a vector of features that we've extracted for a particular image pixel. And we can do this for every example. So we can do this for pixel I. And then depending on the kind of classification we're building, we'll end up using this to make a classification decision for every pixel. So if I build a model using phi of x instead of just the image intensity x by itself, what you find is that it works pretty well. So what I'm showing on this slide is, so I'll answer the question in 2 seconds. I'm showing precision versus recall, which are measures of sort of how well a certain classifier is doing. And the reason that I have a curve instead of a single number is instead of just showing thresholding at 0, I'm actually going to move the threshold around. So what I'm showing is sort of as I change the threshold at which I decide +1, -1, how does precision and recall change? If I do this across a whole bunch of different kinds of features, I get different kinds of results. And the main thing that we want to take away, so for precision and recall, higher is better. So you want to be sort of in the top right. In this example from 2004, humans do pretty well on this task. So they're able to tell the foreground and background because they can use a lot of contextual cues and sort of a lot of information about what else is around the image. You can show that you're approaching the performance of humans by using these extracted features. Modern methods in circa 2020 do even better. So you expect the gap to be much closer. But still, the idea here is I've taken my data, my original image. I'm interested in classifying every single pixel. I've converted this pixel from just the pixel value itself to something that captures neighborhood information. So I've extracted a set of features for that pixel. And I'm now building my classifiers based on the features for that pixel. Phi of x is generally not the same length as x. So the W that I learn, the weight vector that I learn when I'm fitting a classifier for x is completely different from the weight vector that I learn when I'm fitting a classifier for phi of x. So phi of x is typically bigger in general. Later on, we'll talk about dimensionality reduction when phi of x can be smaller than x. But in most cases, and in all the cases we're going to talk about today, phi of x, which is the sort of feature extraction of x, is generally trying to add more context and more information from the original inputs. And so it tends to be much bigger. So for instance, in this example, x is of size 3, so it's an RGB value for a particular location, where phi of x is in the tens to hundreds. So it's quite a bit bigger. Okay. Other questions on the setup and the results? If you want to classify every single pixel, I don't understand what p greater than x is. Could you ask the question again? The last question. If you want to classify every single pixel, does that cause p greater than x? Could you ask again? Or maybe ask offline. I don't understand the question. Okay, so the key takeaways from this discussion. One, it's well known that in practice, that often the performance of machine learning algorithm, at least standard machine learning algorithms, can depend a lot on what features you select. And in fact, the feature you use can have much more impact than the algorithm you use for classification in many kinds of settings. And so for a very long time, most of the work in machine learning was trying to come up with sort of a good feature set. Most of the work in applied machine learning was trying to come up with a good feature set for that sort of best captured the applied task that you are interested in. There's an interesting question about the concavity of human curves. Why the curve is concave, that's interesting. You know, no, I've never thought of that before. So the question is, the human curve is sort of concave, human performance, whereas all of the machine performances match what we typically expect in terms of precision recall? That's a good question. I don't know the answer to that question. I think it's worth taking a look at the paper. I bet that they have some discussion of it there, but I don't know the answer to that question offline. It's a good question. Okay, back to the lecture. So selecting good features is key to good performance, often. The most common approach in practice is by domain experts knowing a lot about the problem that they're solving and using that to come up with sort of heuristic sets of features that are likely to capture what's important about the task that they're solving. So in future lectures, this is in. So in future lectures, we'll talk about deep learning methods as alternatives to feature extraction and talk about how they can help automate some of this effort in trying to find good features. So to summarize, sort of for a long time, most of the effort in applied machine learning was trying to come up with good features. I think now it's a mix. In some settings, you still get the best performance by very careful feature selection, but particularly in computer vision and lots of applied settings, it's now true that you get the best performance by using something like a deep learning method, which we're going to interpret as automating feature extraction. And we'll talk about that in a few weeks. Okay. So a bit of caution. Adding features doesn't always help you get better performance. It is possible to add features that can hurt performance. Does anyone know how this can happen or want to guess why adding features isn't always better? So, okay, so overfitting is a good answer. Too many parameters, irrelevant features, collinearity. So all of these actually can easily happen. So all the answers actually look good to me. So in particular, to talk about irrelevant features, it's easy to add features that are pure noise. So they don't actually, they're not causally related or sort of actually related to the thing you're trying to classify. But on a small sample that you have, they happen to be correlated with the label. And so if you have this situation, you can end up thinking that a feature is important, but it actually isn't. So more features doesn't always lead to more performance. As we go through lecture, we'll talk about how to evaluate whether sort of a certain modeling framework is likely to work well. So we'll talk about cross-validation as one of the ways that we try to evaluate whether we have a good feature set, good sets of hyperparameters, things like that. So we'll talk about that down the road. Dimensional reduction can be useful for choosing features. We'll spend a few lectures on some methods for dimensional reduction. I think it's also true that some algorithms don't work as well with high dimensional features, particularly algorithms that are sort of easily noise prone. So KNN with a small k, I think, is a good example, where if I have if I have lots of features, so high dimension and few samples, I can get in trouble. Linear models, this is also true, like what we've covered so far. Particularly if one is not careful about regularizing. You can easily end up in a situation where more features leads to worse performance. Okay, any questions about feature extraction? So most of what we've covered went through an example I give you where we had a task of a binary classification task for an image. And what we did was we went through how the original features were not effective for this task. However, we could easily construct features such that now in the augmented feature space, the prediction problem is better defined and we end up with much better performance. Okay, so I'll hold off one more second for questions. If there aren't any more, I will move on. So let's go back to linear classification, which is what we were talking about last time. And now we're going to use our phi of x instead of x, because now we know what phi of x is. So we talked about linear regression for classification. So Our labels, our targets are binary. Again, we're going to choose +1, -1 for convenience. Again, you can pick any set of sort of distinct targets are fine. You can always transform between one and the other. It's a good exercise, by the way, for you to quickly check that you understand how to go between, say, a -1 +1 coding and a 0, 1 coding. It's good to sort of check that you can do that transformation easily. So let's consider a one-dimensional problem, a simple model for this. So in one dimension, X is only one feature. So I'm interested in predicting from that single feature. My prediction is going to be the sine of W times X plus my bias term. We're calling this W0 here, but we can also call it B. Let's fix that. Okay. So what might regression look like? So remember, Y takes only two values. It can either be +1 or -1. So if it's either +1 or -1, suppose we're in a simple situation where all of the +1s are to the right, all of the -1s are to the left. Is this question about explaining again? Can someone ask her? There's no question. What am I explaining? A magenta triangle. Okay, so the triangle is at 0. So this is the point that you would make a decision. So again, what are we doing? So I'm giving you an X. I'm looking at the output of a linear regression from X to Y. This axis is my X. This axis is my Y. Y takes two possible values. It's either +1 or -1. And I'm in a nice, clean classification setting where all of the -1s have small values of X. All of the +1s have big values of X. And so if I fit a linear function, this is a linear function on XY space. The result of that linear function is going to be a line, right? And so this line is going to look, on this data set, on this XY data set, the line is going to look like this line I drew here. And if I apply my prediction threshold to this line, I'm going to put a threshold right around here, right? So the sign is positive to the right and is negative to the left. And I'm going to end up with perfect classification for this problem. So you can see this a couple of ways. I went ahead and drew Y and X here, but it's often a lot more intuitive to just look at X by itself and ignore the Y. So I'll draw the same thing, but in one dimension, ignoring the Y. I'm going to make the +1s pluses. And then the -1s, I'm going to make maybe crosses. That's bad. I'm going to make them plus and minus, actually, but with circles around them. Maybe that would be better. Okay. So if I do this, if I plot the same thing on this one-dimensional plane, then this will look like a bunch of negatives here. And then a bunch of positives here. And this is my 0. And to the right, I'll make a prediction of positive. To the left, I'll make a prediction of negative. And in this setting, I get a perfect classification for this task. Is this clear to everyone? What happened or what's going on? So I'm applying straight linear regression to this classification task. So what do you do if Y is 0? So remember, Y can only take two possible values. Y can only be +1 or -1 by definition. So in this setting, Y cannot be 0. Your prediction can be 0. So W transpose X plus W0 can be 0. In general, what you do if you have 0 is you pick a rule and you stick with it. So the sign function you can either define as greater than or equal to, or just greater than by itself. So If you have exact zero, you decide what you're going to do ahead of time if you have zeros, and just stick with that all the way through. It doesn't actually matter. In theory and in practice, it doesn't matter that you sort of have this ambiguity at zero, because you almost never get the outputs to be exactly zero. So you almost always greater or less than zero. How do you pick the threshold? So everything we're going to talk about today, we're going to assume that you just threshold with the sign. So threshold is always at zero. So you take your prediction, you always threshold at zero. If it's greater than zero, you're going to predict +1. If it's less than zero, you're going to predict -1. For definitely everything we'll talk about today, and most of what we'll talk about in the class, our predictions are going to be sine of W transpose X. For this model, so this is a one-dimensional model. So in one dimension, meaning X is in one dimension. So X is in one dimension. So which means W is in one dimension. So everything here is a scalar. So W is dimension 1, X is dimension 1, a number. So W is a number, X is a number, W0 is a number for this example. We're just using this for illustrations. This is the 1D model that we talked about. Just to, I guess, think of the simplest setting where we could try to explain what's going on. In practice, of course, you're rarely going to deal with one-dimensional problems. In almost every example, almost every real setting, D is going to be much bigger than 1. What happens if the lines overlap? So I think what you mean is if you have some examples, if you have some pluses on the other side. So if I have a situation where, say, I have some pluses here, some points here, for instance. So suppose I have some points on the other side of the line. What happens to the prediction? Yes, okay. So in terms of what the optimizer will do, we'll talk a little bit about what the biases of, the short answer is it depends, and we'll have to actually try it to see what happens in a real example. But I could talk a bit about what sort of general patterns to expect if you have points on the other side. So we'll talk a bit about some settings where this happens and how classifiers handle it. In general, the model will still fit. So it'll still find the best fit line between Y and X, even though now there's this additional point that doesn't fit the pattern. So if you've ever seen sort of any kind of linear fit through data, even if you have sort of extraneous points all over the place, the linear fit is still the best. It's still the line that minimizes the squared loss. So whatever minimizes the squared loss. In practice, what this means is that it will tend to shift a little bit to the left if there are a bunch of extra points on the left, because that's the solution, the line that has the minimal squared loss. So that's what will happen in practice. In terms of prediction, what will happen is that it will make a mistake, right? So if I pick a threshold of 0, then points that are on the other side will be predicted as negative, even though they're positive. So that's an example of an error in classification. Okay, any other questions on the setup? Okay, so what will happen, to follow up on that last question, what do you expect will happen if I fit a linear, this is not a good question to ask by chat, but I'll try anyway. What might happen if I fit sort of a line, say, to minimize the squared error for data that looks like this? So what's the difference in this data? It's still, all of the pluses are above 0. So all the x's that correspond to +1 are above 0. All of the x's that correspond to -1 are still below 0. So this is something that can be easily fit with a linear classifier, because in this case, I'm just picking a threshold. However, there's a gap. And in particular, I think more importantly, there are many more positive points than negative points. Okay, so some of the points in the middle are going to be, yes. So in particular, some of the points in the middle are going to be classified as negative. If I fit a linear regressor to this example, what I'm going to see is that the resulting prediction, so the resulting classification, is going to put the threshold, instead of having the threshold be exactly at 0, is going to end up here. So remember, this is controlled by W0, which is this bias term that pushes us to the left and to the right. All right. So that was supposed to look like a line. Anyways, so we're going to make a mistake. We're going to make a mistake on all of these points. We're going to make wrong predictions on. Sorry, not all those points. All the points to the left of that line. So all these points will end up making a mistake. Okay, so in particular, the decision boundary has ended up shifted. So in this, the question was, what does W do for us if the classification is determined by W0? Remember, this is a very toy example. So W controls scaling, W0 controls bias. And here, since it's just one dimension, the scaling doesn't matter that much. Of course, once you go beyond one dimension, W is actually extremely important, because that tells us how to trade off different features and building the linear classification. So this example was chosen for illustrative purposes to make it hopefully easier to visualize what's going on. Though I think it's possible, so I want to avoid it being misleading, because it seems to suggest in this example that W doesn't matter. It doesn't for this simple 1D case, but it'll definitely matter in general. So it's actually quite important. Okay, so why does this shift happen? So I've alluded to this a few times. Why does this shift, why does decision boundary end up shifting? Using the same, so remember what I'm doing is least squares. So least squares plus this decision rule. Why is the decision point not 0? So what happens, the reason it's not 0 is that W0 shifts the bound. So the optimal, if I minimize the loss function, I find the optimal W and W0. What I'll find is that W0 is not going to be 0. So it's going to lead to a shift in where I put the threshold. And the shift is going to be determined by whatever value W0 gets. So one answer was that the shift is due to bias in the data. Yes and no. Shift because it's trying to accommodate all the X's. Yes, but it's in this specific way. So it's trying to find the best fit line. And it's trying to, in particular, it's trying to minimize the squared loss, which is what we talked about last time. And one issue with the squared loss is that if I have large positive values, they're as bad as large negative values. So remember, the squared loss penalizes both kinds of errors. So in this setting, one way to interpret what's going on is somehow in this region of space, the prediction is a large positive value. This leads to a large squared loss. And so the model tries to compensate by shifting the weights to the right so that the loss for that, the data on the right is a little bit smaller. So it's not as bad. So in pictures, let's go through this in a bit more pictures. So I'm minimizing squared loss on data. So this is the same example as what we talked about over the last few classes. And what I want is to find a setting of W and a setting of B such that the squared error is small. I apologize for the switching notation. I'll try to fix it. Where I put W0 for the previous slide and B in this slide. I wanted to use B for all of the lectures. So W here is the weight and B is the bias. So same as previous lectures in this class. So my goal is to try and find a setting of W and B that minimizes the squared loss. So that's what I'm targeting. That's what I'm hoping to solve. And in particular, I want those values. So I want the argument that actually achieves this minimum, as we talked about last time. So remember that squared loss is literally sort of the difference between the data point and the line squared. So it's the value of y minus the prediction, which is W transpose X minus B. So this line is W transpose X minus B. And the difference between the two is going to be the error, and I have this error squared is the thing I try to predict. Is the thing that I'm evaluating as the error. So for a line like this, an error is all the gaps between the data and my prediction, my function, W transpose X minus B. So in So in the perfect classification case, we end up with a setting where the task that we're solving, which is finding the best fit line, happens to align well with good classification. Whereas in the second task, and we'll talk about this a little bit more in a couple of slides, I have the opposite situation where finding the best fit line, so minimizing the squared error, actually leads me to make a mistake. So let's go in a bit more detail just to flesh this out a bit. So remember, my goal in least squares for classification is to minimize the squared error. So my loss function is y minus W transpose X. So I've converted now from the one-dimensional W and B to the sort of multivariate version where I have W transpose phi of X, this feature construction that we talked about at the beginning of the lecture. So I think there were more steps there. I'm not sure what happened. Okay. So we talked about this last time, but you can do a bit of algebra, and you can rewrite this as 1 minus y times the prediction, right? So the reason you can do this is that if y takes either value +1 or -1, then y squared is always equal to 1. So if y is 1, then y squared is 1. If y is -1, then y -1 squared is also 1. So you can easily rewrite the squared loss as 1 minus y times the prediction. And for convenience, we're going to call this prediction f of x and w. So now let's try to build some intuition about how the loss function behaves to see sort of why it ends up actually behaving badly in settings where the data is perfectly classifiable. So its data is perfectly separable. So here's a quadratic loss. So it's centered around 1 because this 1 is on, is sort of, the thing we're trying to hit is to make everything equals to 1. Now, ideally what we want is that the sign of y and f of xw is the same. So they both have the same sign. In practice, what we find is that if the value of the prediction is really big, so like I talked about last time, the value of prediction is say somewhere out here, then I'm going to pay a loss that grows quadratically. So it grows very quickly with, with the prediction value. So interestingly and importantly, it grows quickly in both directions. So both when I make good predictions and when I make bad predictions, large values of f, which push me away from 1, actually end up leading to bad outcomes. So squared loss actually penalizes samples that are very easy to classify. And very easy here means that they have sort of large scores, right? So if I make a prediction, the prediction is 1,000,000 and the true value is 1. The sign of 1,000,000 is +1. The true value is 1. This should be a good thing. But squared loss will penalize you 1,000,000 squared because you're 1,000,000 squared away from 1. and that's going to be the cost of making that prediction. So in particular, it's well known, to answer the last question, that squared error is very sensitive to outliers. So points farther away tend to have bigger and bigger impacts. This is the whole point of, like, this is how quadratics behave, right? So it actually grows with the squared of the value. So exactly, yes. Points that are far away have a big impact, and in fact, the impact that grows with how far away they are. The squared loss is weird for classification problems. It's great for regression problems. So in regression, remember, we want to get the value. The value is some real valued prediction. We want to get that prediction correct. That's fine. But if you're interested in classification where all you care about is the sign of the output, so you just want to get the sign correct, either get the sign to be +1 or get the sign to be -1. Squared loss behaves a bit weirdly because it actually penalizes you for being really confident about your prediction, which seems like a bad thing. So we're going to try and we'll use this intuition to motivate an alternative method or alternative loss function that behaves better with the prediction. The next question is, or one question is, if we only care about the sign, why don't we put the sign into the optimization problem? Can anyone guess an answer to that? We haven't gotten to this yet, but I'm curious if someone already knows. Why can't we just, so instead of solving this problem with y times w transpose x, why don't we just throw the sign in? Yeah. So in the middle, we're going to have to solve this using, we'll talk about this a little bit today. We'll spend a lot more time on this later. But sign functions are not easy to optimize. In fact, once I throw a sign in there, the problem becomes, you can show that the problem becomes combinatorial, and it actually is sort of provably hard to solve it exactly. And so you can do heuristics to do something reasonable, but it actually is quite tricky. Why not use absolute value? That's completely reasonable. It doesn't solve the problem, but that's an interesting idea. We'll talk today about a different choice that solves the problem better. But the intuition was, instead of using quadratics, why not use something like a linear function? So that will sort of look roughly maybe like this, which is good because it's a bit better behaved. It still penalizes you for being correct or wrong, but it only penalizes you linearly with how correct or wrong you are instead of quadratically. So as the value gets big, the gap between linear and quadratic can get really large. So linear is maybe a better answer. Linear still has issues because it's still non-differentiable at 0. We're going to get to sigmoids. I think lots of folks in the chat have the right intuition. So we're going to get to a loss function that has a shape. What we're hoping for is a shape that looks something like that, where if you're wrong, it penalizes you to push you in the right direction. If you're correct, it doesn't. It penalizes you either nothing or very little for making the right decision. So right decision, good, no penalty. Wrong decision, bad, penalty, so that you can try to make better predictions. It's also worth contrasting this with the 0-1 loss function. This is the exact prediction loss function. This says, I give you a loss of 1 for making any mistake, give you a loss of 0 if you're correct. And you can see that these two behave quite differently. So the 0-1 loss function is a step function. It is not differentiable. It's not easy to actually apply to real problems. So instead we optimize with these alternative loss functions, things like squared loss and other losses we'll talk about today. So how do we fix this problem? So I already see some solutions in the chat, but we'll go through in some detail. So one way that I like to present a fix to the problem is to go back to probabilistic motivations, because I think for many people this is somewhat intuitive. So we'll start with a probabilistic model, and then we'll eventually just think about this as loss functions. So let's start with a probabilistic model. So remember, when we were trying to motivate linear regression, what we said was that linear regression is equivalent to a Gaussian model where the mean is linear, right? So the mean is a linear function plus Gaussian noise. So we're going to try and do the same thing for classification problems. So remember again, we said I'm going to assume that the probability of my output given my input, so P of y given x, is going to be a linear mean and then a Gaussian distribution around the mean. So if you want to write this, it will look like a Gaussian with mean W transpose phi of x and variance sigma squared. Right. So if this is my model for my data, then I end up with a PDF that looks like the thing on the top. Okay, so that's a simple case. And if you remember, what we said was that this looks like a little sort of PDF bump around every point. So this ends up acting like a linear function, which specifies the mean of my input-output relationship, and then Gaussian error around it. So now we're going to shift gears and say, suppose our output is +1, -1, which we know that it is for classification problems. So what's a good probabilistic model for binary valued outputs? Does anyone remember what a good probability model is? If I'm interested in binary random variables, okay, exactly. So a good probabilistic model is a Bernoulli model. So I just write this here. So what it does is P y equals 1 is going to be sort of, it's going to be some probability. Typically, you call this theta. And P y equals -1 is equal to 1 minus theta, where theta is between 0 and 1. Right. So this is a coin flip model, right? This says I'm going to flip a coin. This coin is a biased coin, and the bias is specified by some parameter. I'm just calling this parameter theta. And depending on whether this coin flip lands as a +1, or sorry, the coin flip is more likely to land as either +1 or -1, depending on whether theta is greater or less than a half. If theta is greater than a half, then I'm more likely to get +1s. If theta is less than a half, I'm likely to get -1s. This is a good model for, this is a good probabilistic model when I have binary random variables. Okay, so there's a question about phi transpose W and W transpose phi. The answer is correct, yes. They're both numbers. It's also, you can swap the order, it doesn't change the result. We'll try to be careful, though we may do this every once in a while. If any of this ends up confusing, please let us know. Okay, so we're partially there, not all the way there. So now we have a probability model for binary variables, but our prediction is of the form f of x is equal to W transpose phi of x, which will give me a number between -infinity to +infinity, right? So this prediction is always going to be something in the reals. Does anyone know? There are many ways to do this, but there's a standard way, which I think came up before. Well, what's the standard way of converting from something in the real to something that I can use as a binary, as a number between 0 and 1? Okay, so we're going to use a sigmoid, and let's talk about it in detail. So in particular, our model for observed data is going to be a sigmoid applied to W transpose X. So this is saying that the probability that my label is 1 is, so the sigmoid notation, you'll see this later on, is sigmoid of whatever the input is. The sigmoid function looks like this S-curve, so sometimes it's called the S-curve. It's a way of squashing the reals into something between 0 and 1. So the output of a sigmoid is always between 0 and 1. The input is any real valued number. So what I do is I start with my W transpose X, my real valued prediction. I'm going to push it through the sigmoid function. This is going to give me a probability, and this is going to be my model of the probability of Y equals to 1. Any questions on this? Is this clear enough? Okay, so this is not a binomial, though it's close. We're using a Bernoulli, but it's close enough. It doesn't matter. So we're trying to motivate modeling labels that take values either +1 or -1. So what we said that was that a good model for a random variable that takes values either +1 or -1 is a Bernoulli, if you remember from probability. And now we want to use a Bernoulli to construct a model. So in order to make it into a model, we combine a Bernoulli with a sigmoid, which now allows us to make predictions and then convert them into probabilities. Okay, so one nice property of the sigmoid is, one nice property of our Bernoullis, but also a nice property of the sigmoid, as we'll see, is that the probability of the opposite events of -1 instead of 1 is just 1 minus. Since there are only two possible events, it can either be +1 or -1, nothing else. So the probability of -1 is just 1 minus the probability of 1, conditioned on x. So this is nice because it actually has a really nice form. You can show that the probability of that y equals -1 given x is just going to be, again, a sigmoid-like function, but then it takes away the negative. So it turns out to have a really nice sort of notational convenience. So we'll work through sigmoids a bit over homework to, if you haven't seen them before, to get more comfortable. But there are common functions that we use for modeling sort of, for modeling things that need to, for trying to convert real value things to probability functions. So does the sigmoid output a probability, or is just the value between 0 and 1? So remember, we're doing modeling. So the sigmoid outputs a number between 0 and 1. We choose that this number represents the probability of y equals 1. And then our job is to find the right value of w, such that it best fits the data that we observe. So our model, just to repeat one more time, our model is P of y given 1, P of y equals 1 given x is given by this function. This is a choice of model. This is generally called a logistic model, if you want to look up literature. So this is a way of modeling observed data. Based on this model, our job now is to find a good setting for W. So this is the learning part of the problem. Okay, so now if I combine, so one nice thing as well is that I combine the +1 and the -1, because all that's different is whether I have a negative sign or not a negative sign. And if I use this +1 -1 coding, there's a convenient way to write everything together. I can write P of y given x, I can simply write as this combined function, because if y is +1, I get the negative value. If y is -1, I get this other value. So it's convenient because this gives me a way to write both cases as a single function. So we fit the W in a way that sigmoid value can be interpreted as a probability. I think that's a good enough. So the question was, we fit W in a way that the sigmoid value can be interpreted as a probability. I think that's a good enough abstraction, though I want to be careful, which is why I'm saying this a bit carefully. So I'll repeat one more time. So we get data. We just have a data set. We're going to choose a model for this data. Our model for the data will use the sigmoid, which gives us a value between 0 and 1. And we're going to interpret the output of this model as a probability. So up until this point, it's a model, right? Just like the same exact thing is in linear regression, where we had a Gaussian assumption for the noise in our linear Gaussian model. It's the same exact thing here. We're choosing to model our observed data as a logistic regression, a logistic function. So this is the choice that P of y given x takes this form. So the question was, can I interpret this as a probability? According to the model, this is the probability, yes. I am being a little bit pedantic, and I think I'm also being a little bit vague. I apologize for this. I've seen this get misinterpreted, which is why I'm trying to be careful. I think the easy sort of short explanation is From the point of view of from the point of view of the model, this is a probability. So this is a probability according to the model of y equals 1 given x. So hopefully that answers the question that you have. Okay, so next we need to find model parameters. So remember, I just give you a data set of size n. I've fixed the model, this logistic model that we just discussed. Now we need to actually find parameters. So the most common thing, what we did last time and what we'll do today, is to choose parameters that maximize the likelihood or the probability of this data set. So there's a question about how we can combine y in the equation. I would say it's a good exercise. Plug in y for the two cases and see if the results match the original model. I think it's a good quick exercise for you to do. So in particular, what I'm saying is if I take, take this result, plugging the two values of y, and check for yourself that you can get the two cases correctly back. 146. Thank you. So we are out of time. I'm going to stop the discussion here. Next time, we'll talk about maximum likelihood and then segue from that into optimization. I think I got a bit carried away. I'll hang around for a few minutes to answer any questions. And we'll start back on this slide in the next lecture. Thank you. I'm going to stop recording.